Let's start. I'm very happy to introduce Steffen Lempp, who will talk about decidability and undecidability in the enumeration degrees.
Well, thanks a lot for coming this late or early or whichever it may be for you. So I want to talk about a project that I did with Ted and Maria over the last about a year and a half. And we've tried to prove one thing and we proved two other things instead. So I'll try to show what's going on. So the topic we were thinking about was decidable and undecidable fragments of the theory of the enumeration degrees. But I don't know how many non-experts in the audience. So the initial two slides may be for the non-experts. So we work with subsets of omega and study their relative computational complexity, and we do this. I want to set this up very formally because I want to sort of advertise a program which was very popular when I was much younger and has maybe a little taken a little backseat to other parts of computability theory. So reducibility is a transfer reflexive relation on the powers of omega, which expresses that A can be computed from B in some sense, and there's various ways one can define computed. I will give some examples later, but I'm sure you know several already. We call two sets A and B are equivalent under this reducibility if we have reductions both ways. And so that means that A and B have equal computational content. The equivalence class of A under this equivalence relation, as it's clear that this equivalence relation is called its degree. And we studied in global degree structures. So the global degree structures, the powers of omega, modulo this identification under interreducibility. And since less or equal sub R is a pre-partial order, this induces a partial order on this here. On this degree structure, and that is the partial order that we work with. And sometimes we enrich it with other things I'll talk about in a second. But let me also point out that sometimes, in fact, quite often, we consider what's called local degree structures. And that's when you take a typically countable subfamily of the powers of omega defined as by some scheme. And you just take the quotient of this subfamily S modulo this equivalence relation, and you get some countable degree structure rather than the size continuum degree structure that you typically get for global degree structures. So, so degree theory studies degree structures as algebraic objects, in particular as partial orders. Sometimes one can expand the language. I will resist the temptation to do that, but I know that, for example, Richard definitely and several others have also looked at expanded languages. But I'm just going to stick to partial order for tonight. And so there's a pattern going on with degree structures. A natural degree structure, you can think of Turing degrees, CE Turing degrees, etc. They follow the following pattern. First of all, first of all, let's look at some basics. I mean, there's usually a least element. This is the stuff which is computable for everything else. So that would be the computable sets on a Turing reducibility or the CE degrees, the CE sets under enumeration reducibilities. Local degree structures generally also have a greatest element, but global degree structures do not in general. D is locally countable, meaning that it has the countable predecessor property, and the degree has the most countable many things below it. D is usually also an upper semi-lattice, but usually not a lattice. So there's a join operation, but not necessarily a meet operation. And join operation generally for most reducibility is defined by just taking the join of the degrees of A and B as a degree of the set theoretic join of A and B, namely code A on the evens and B on the odds, and you get the join. That's a natural join operation, and for almost all reducibilities, this turns out to be just the right way to do it. Most degree structures also support a jump operation, Turing jump, enumeration jump, etc. I will not talk about that very much, but just remind you of, that this is a function which is strictly increasing, so a is less than a jump, and it preserves non-strict ordering. So a less than or equal b implies that a jump is less than or equal b jump. Okay, so that's the stage. So now let me talk about the complexity of the degree structure. So the natural degree structures tend to be very, very complicated algebraic or objects. So unlike the initial results from the 50s, where people thought that degree structures were quite simple, and then in the early 60s, Schoenfeld even put out particular, and Arthur Rogers put out specific conjectures about homogeneity and various other things about degree structures. But it actually turns out they're very, very complicated, and they generally follow this pattern. So the first order theory of the degree structure, D, is undecidable, but it's actually worse. It's not just undecidable, but generally for global degree structures, the theory is as complicated as second order arithmetic, which of course is a theoretical upper bound. And for local degree structures, which we're assuming countable, it usually turns out to be as complicated as first order arithmetic. So these degree structures are as complicated as possible even in a language of just partial order. So generally, computability theorists try to figure out at what quantifier depth undecidability starts. And so we study fragments of the first order theory and count quantifiers. And an easy observation generally is that the existential theory of a degree structure is decidable. That's because all finite partial orders generally embed into any natural degree structure. And that makes it pretty simple to see that, of course, the E theory is decidable, because you just check whether or not the existential formula that you're checking for is consistent with the theory of partial orders. So that's the first step. It turns out that for many degree structures, but we don't know it for all of them, but for many degree structures, we even know that the AE theory is decidable. Now, of course, remember, we're not talking E and A and EA and AE theory and whatever. These are all complete theories, because there's theories of one structure. So therefore, it doesn't really matter whether you talk about the AE or the EA theory. But I'm just talking about the AE theory because that's easier for me to think about. So the AE theory is often decidable, but the proof can be quite complicated. And I'll talk about that in more detail later on. And then if you go one more quantifier level up, if you go to EAE theory, so this is the set of all formulas with a block extension, block universal, block extensional quantifiers followed by something quantifier free. These can usually be shown to be undecidable, and I will show you a little bit of technique if you haven't seen this before, how one does that kind of thing. So let's see. Let me give you a quick overview. I'm going to look at 7 typical degree structures. And I'll look at the complexity. I'll look at what's known about the decidability of fragments. So for M-reducibility, we have the global degree structures. The global degree structure was shown by Narod and Shor in 1980 to be as complicated as second order arithmetic. This was, I'm suppressing here the fact that, of course, a few years before, somebody else, and I don't remember at the moment, somebody else had shown that that the theory was undecidable. I think it was Lachlan. But anyways, the ultimate goal was to show the complexities as complicated as second order arithmetic, and this was a result due to Narod and Shor. Jokestev in a 1979 paper showed that the AE theory is decidable, and Nice in a 1996 paper showed that the EAE fragment is undecidable. For the CE mini 1 degrees, remember, if you're reducible, M reducible is 0 prime, then of course you're just CE. Nice showed in 94, so quite a bit later than the Roadshow result, that the complexity of the CE many 1 degrees is the same as first order arithmetic, and the results of Yokchev and Nice also work in pretty. It's the same paper. They work almost verbatim for the global and also for the local structure of the CE many 1 degrees. Moving on to Turing reducibility. For the global Turing degrees, Simpson in 1977 showed that the theory is as complicated as second order arithmetic, and Lerman and Shor independently. So Shor actually wrote it up. Lerman did not. He didn't write it up until a few years later, and when he published his book, showed that the AE theory is decidable. And Lerman and Schmerl, this was published in Lerman's book, showed that the EAE fragment is actually undecidable. And that was actually the first time that an EAE fragment had been shown undecidable. And I'll explain a little bit about the technique in a little bit. For the delta 0, 2 Turing degrees, so these are the Turing degrees below 0 prime, Shor in 81 showed that the theory is as complicated as first order arithmetic, and the AE theory was shown to be decidable by Lerman and Shor in a joint paper in 1988 to be decidable. And the proof of Lerman and Schmerl also works for the delta 0, 2 degrees in almost the same way. I'll talk a little bit about what the difference is. Actually, no, that part was the same, but there is a difference in the AE theory proof for the Turing degrees and for the delta 0, 2 Turing degrees. Okay, so this is the Turing degrees of these two structures. There's one more local degree structure that's dear to my heart, the CE Turing degrees. So the complexity of the theory is the same as first order arithmetic. This is the result of Harrington and Slayman from 84. We do not know the AE theory, whether it's decidable or not. So we have to go back all the way to 63 when Sachs observed that the E theory was decidable, and that's just because you can embed any partial order, any final partial order into the CE Turing degrees. He actually explicitly stated that way first. I think he may have even observed it a little earlier, but the first time I think it appeared in print was in the 63 publication. And it was quite a bit later that Andre Nice, Ted Slayman, and I were able to show that the EAE fragment is undecidable for the CE Turing degrees, which is quite a bit harder than for the other degree structures, because now we're talking about dense partial order, whereas the others are not. So I'll talk about that in a little bit in more detail. I want to move on to a couple more degree structures that I've been particularly fascinated by lately, partially due to Maria's influence. So the enumeration degree, so there's the global structure of the enumeration degrees. That was shown to be as complicated as second order arithmetic by Slayman and Wooden in 97. And for the, again, we don't know the AE theory. That was actually the initial goal of our project to decide the AE theory. We were unable to so far, and I'll explain why we were unable so far. So we have to go back to 1972 when Lagerman observed that this result of Sachs actually carries over to the enumeration degrees, the global result. So Maria, Ted, and I were hoping to show that the AE theory is decidable, and by accident, we were able instead to show that the EAE fragment is undecidable. We just, all of a sudden, it just came out of nowhere. So we were kind of surprised by that, but it worked out. And so this is the paper which is on our websites, and it's been accepted for publication. So it should actually be in print shortly. For the local degree structure of the E degrees below 0 prime, which is the same as the sigma 0, 2 E degrees. there is the result by Gunchev and Maria Soskova that it does complicate as first order arithmetic. Lagerman's observation also works for the sigma 0 to E degrees. And my student Tom Kent in his thesis in 06 showed that the theory of the EAE fragment of the theory is also undecidable. Again, so note the gap that we have here. I don't know if you can see my cursor, but the gap that we have is the fact that we do not know the status of the AE theory for these 3-degree structures, for the CE Turing degrees, for the enumeration degrees, and for the sigma 0 2 enumeration degrees, which is quite annoying, and we've been trying to work on it. I've spent a lot of time earlier on in my career about the CE Turing degrees, and lately I've been working more on the enumeration degrees, both local and global, but have been unable to resolve any of them so far, but one step at a time. So let me talk a little bit about techniques, how one shows these kinds of results. So the undecidability of the EAE fragment is generally shown by what's called a niece transfer lemma, which he stated in a 96 paper, and I'm only quoting a special case here, but I do not want to give the impression that this was Nice's original work. I mean, this really goes back much earlier to work of Trachtenbrot, and then later on, there was a seminal paper by Yershov, Lavrov, Taimanov, and Teitzlin, and they studied the common theories of finite of classes of finite structures like partial orders and so on, and lattices and distributed lattices, all kinds of finite structures like that. So they didn't actually count quantifiers in that paper, but they did show hereditary undecidability. And it was Schmerl's insight when Lerman was writing his book to actually be more careful about the quantifier count. And that's how Lerman and Schmerl were able to establish these 1983 results about undecidability of the EAE fragments. The technique was then crystallized by Nice in this, what he called the transfer lemma. He has it more generally, but let me just tell you what the special cases that we will always need for the results I'm quoting here. So the setup is the following. You have a class C of finite structures like lattices or distributive lattices or partial orders, linear orders, whatever. Suppose this class of finite structures is existentially definable with parameters. So that means there's a formula which defines the universe on which your code is in the degree structure. There's also an existential formula defining equality and inequality. So you can both define equality and inequality by an existential formula. And then for any let's say it's a relational language, for any relation symbol, you can define both it and its negation by an existential formula, all with parameters, with final many parameters from the degree structure. That's the first assumption. So if this class C of finite structure, which is E definable with parameters in the degree structure. Second assumption about C is that if you look at the common AEA theory of C, now remember, C is a collection of different objects, so therefore it doesn't have to be, this is generally going to be an incomplete theory, but this AEA theory is what's called hereditarily undecidable. So that means not only is the AEA theory undecidable, but any subset of it which contains all valid sentences is also decidable. Undecidable. That's what hereditary undecidable means. So under these two assumptions, E defined with parameters and the common AEA theory of C is hereditary undecidable, then Nice is able to conclude that the EAE theory of the degree structure is undecidable. This is basically the most common technique how to show that the EAE fragment of a theory of a degree structure is undecidable. And so let me just mention how this is done in the case discussed earlier. So the class C of structures that's used in the results above is one case is the class of all finite distributive lattices, which can be coded as initial segments in the many 1 degrees, in the CE many 1 degrees, in the Turing degrees, and the delta 0 2 Turing degrees. So therefore, not only is it are the structures extensionally definable, they're actually quantifier free definable with a single parameter. The parameter is just the top of the cone, which is the range of the embedding. Okay, so that's the simplest case for undecidability. It gets more complicated when you do it for the enumeration degrees. And this is this result that Ted, Maria, and I were able to get recently. We were able to show that all finite distributive lattices can be coded as intervals in the enumeration degrees. Now remember, because of a result by Guttridge from around 1970, the enumeration degrees are downward dense. So there's no hope to show to proceed as the first spool of initial segments, because every initial segment is going to be infinite. But you can at least have that there are intervals which are of any of the type of any finite distributive lattice, and that's good enough to allow you to apply Nice transfer lemma again with a quantifier-free definition of the finite structure, but now using two parameters, namely the top and the bottom of this interval. For the other 2-degree structures, so this is for the CE Turing degrees and for the sigma 02 enumeration degrees, things are quite a bit more complicated because these are dense partial orders. So in that case, of course, you cannot hope for just coding finite structure as an interval, and you have to use something more complicated. What actually has been used for both the CE Turing degrees and for the sigma 02 enumeration degrees is to code finite bipartite graphs in a length without equality, and then left and the right domain are non-empty. So that is the class C of structures you're coding, and you're coding it in a somewhat delicate way because you only allowed finally many parameters. I think it's like 4 parameters, something like that. So you only allowed finally many parameters. So therefore, you have to be very careful how you code this in order to get it just right. So basically, every element of the graph is coded by an extensionally definable set of degrees in the CE Turing degrees and similarly in the sigma 02 enumeration degrees. So that's all I want to say about the EAE fragment. So for the 7 structures I talked about on the previous slide, we know that the EAE theory is undecidable. Let me now turn to the AE theory, where we only have partial results. So one can translate the AE theory to the following algebraic question. So this is a problem which is equivalent to deciding the AE theory. The problem is the following. Suppose I give you finite partial orders P and order extensions Qi. So these are various ways of extending P, finally many. And now what you have to decide is, given P and the Qi's, does every embedding of P into the degree structure extend to an embedding of Qi into the degree structure? This is as a partial ordering only. And of course, which particular Qi you're extending the embedding to may depend on the particular embedding that occurs for P, right? So you have to be careful about, you really have to allow several different possible ways of extending in some cases. And we'll actually see one particular case in a second. So this is the sort of the blueprint for deciding the AE theory. So let me start with the easiest case. For the many 1 degrees and for the CE many 1 degrees, Joktev proceeded as follows. He took the finite poset that he started with, and he extended it in a minimal way to finite distributive lattice. Now remember, the many 1 degrees, the CE many 1 degrees are distributive upper semi-lattice, so therefore it is okay to extend P to a finite distributive lattice. You do it in a minimal way, and now you extend, you embed this finite distributive lattice as an initial segment into the degree structure, as an initial segment. And then any embedding of that L can be extended to an embedding of some finite partial order Qi, which extends L as a partial order if and only if, first of all, no new element in Qi is below an old element of L, because after all, you have an initial segment. And secondly, Qi respects the joints in L, meaning that if Qi is above two elements of L, it has to be above the joint in L. Okay. Now, of course, I'm sweeping a little bit under the rug because there is a step where you have to extend P to L, and of course, there could be some elements in Qi that necessarily have to occur in L, and those would be in Qi minus P. But I'm just taking the easy way out by saying, okay, just extend P first to a finite distributed lattice L, and then things work out very nicely. Notice, by the way, that there's really only one particular, that you could just do this for n equal 1 in this case, right? Because all you're asking for is some finite partial order which is not below old elements and respects joints. That's all we need. So n equal 1 is equal to arbitrary n for the problem up there. For the Turing degrees, Lerman and Shor used the same kind of method, except instead of extending P to a finite distributive lattice, they extended P to a finite lattice in a minimal way, and then did proceed exactly the same way as Joktev. And for the delta 02 Turing degrees, things get more complicated. Now you cannot have just one partial order anymore. So what Lerman and Shor did is they extended, they first of all, they took this L, and now they embedded L in two different ways. First of all, as initial segment, that'd been known for a while, but the other thing is actually was a new proof at the time. They also embedded the lattice L almost as initial segment, except that one was not minimal above the elements above the coatoms in L, but one got mapped all the way to 0 prime, and the join of any two elements which join to a 1. But sorry, the image of any two elements which join to 1 in the lattice get mapped to delta 02 degrees, which join the 0 prime in the Turing degrees. So it is a lattice embedding which is essentially initial segment embedding, except that the top point is moved from the from way low all the way up to 0 prime. Okay, so this is so they had two different embeddings, and that allows you to block different kinds of extendabilities, and now they were able to show roughly the same way as Joktev in the middle of the slide. They were able to show that they can now analyze exactly when so you need two partial orders QI. You need a QI and a QJ in order to block fully. Anyway, so that's the procedure for deciding the A theory. So these are the four structures that I discussed where it's possible. So what goes wrong with the other structures? Well, there are two well-known subproblems of the AE theory. One of them is called the extension embeddings problem, which is a little confusing of a name because really it's the same problem as the one as for the AE theory, except that I'm setting n equal to 1. So I just have a single P and a single Q extending P, and I'm asking, does every embedding of P extend to an embedding of Q? Okay, this is of course clearly a subproblem of the AE theory. And the other famous subproblem of the AE theory for degree theory is the lattice embeddings problem, namely which finite lattices can be embedded into the degree structure, now embedded as a lattice, meaning that you preserve join and also meet. So remember, meet is not always defined in the degrees, but it can be sometimes exist in meet. So you have to figure out what finite lattice can be embedded as lattices. And notice that again, this is a subproblem of the AE theory, because what you do is, if you look at the way I phrased it with the QIs, you look at P which is your lattice, and now you look at one-point extensions which test various joints and meets. right? So you challenge various joins and meets to not exist as the lattice prescribes, and that gives you an AE problem. So therefore, these are clearly subproblems of the AE theory, and here's what's known about them for the three degree structures that I discussed earlier. So the extension of embeddings problem is actually decidable for all three of the degree structures. Slayman and Soar 20 years ago showed that for the C-Turing degrees, there is a decision procedure. And it's quite a delicate decision procedure. I mean, it's a multi-step decision procedure. It's not so easy. For the enumeration degrees, this was actually a byproduct of Maria, Ted, and myself trying to figure out the AE theory. We were only able to show the extension of embeddings problem as a byproduct. Now I'll indicate later what the technique might be, but it is somewhat delicate again because it's a multi-step problem. I mean, there's like the case analysis with about 6 or 8 cases, and for the sigma 0-2 degrees, Ted, Andreas Sorby, and I were able to show that in about 15 years ago. And this was kind of modeled on what happened for the C-Turing degrees with one extra condition, which is due to it's a generalization of what's called the Amat pair. I don't want to get into details, but it's a generalization of that particular problem that led to a full decision procedure for the extension of embeddings problem. Now for the lattice embeddings problem, this is of course a famous open problem for the C-Turing degrees. It is wide open, has been open for 50 years now, and the last progress that was made, I think, is a 2000 paper by Lempp, and ever since people have, I think, probably stopped working on the problem because there's just no, people don't run out of ideas. So maybe some of the younger people should look at it and see if they have any ideas. The lattice embeddings problem, so for the C-Turing degrees, it is just really, really, really hard. It is really, really simple for the enumeration degrees, for the sigma 0-2 enumeration degrees. Andreas Sorb and I showed 20 years ago that all finite lattices embed as lattices. In fact, they embed as lattices where you map every element of the lattice to a low degree, except that the element 1 gets mapped to the degree 0 prime in the enumeration degrees. Okay, so it's about as nice an embedding as you can possibly get. So the Lachlan diamond theorem definitely fails in the sigma 0-2 enumeration degrees, for example. Okay, so that's those are the subproblems. Now let me talk a little more about how we were able to show the two results that I mentioned, the extension of embeddings problem for the global enumeration degrees and also the EAE theory for the global enumeration degrees. So there's a main technical result, which I will state on the next slide. And there are 3 precursors to this result. One of them is a result by Cooper, which was improved upon by Calhoun and Slayman a few years later, that the pi 0-2 enumeration degrees are not dense. Namely, there are degrees A less than B such that there's no degree in between. So the difference, by the way, between Cooper and Calhoun Slayman is that Cooper only showed it for the enumeration degrees. He didn't count exactly with a quantifier. I think there's a pi 0.7 enumeration degree, something like that. It was a fairly high up in the arithmetical hierarchy, whereas Calhoun and Slayman were able to show that actually there are 2 pi 0.2 enumeration degrees with no enumeration degree in between. When the situation like this happens, by the way, we call B a minimal cover phase. Minimal cover just means there's nothing in between. The next result along those lines was due to Kent, Louis Pye, and Andreas Sorby 15 years later, where they show that there is a pi 0-2 enumeration degree B, which is a strong minimal cover of a degree A. So that means that not only is A less than B, but also every enumeration degree, which is strictly below B, is less than or equal A. So one way to think about it is that the cone of degrees less than or equal B can be split into 2 parts. It's singleton B and then everything below A. Nothing to the side. There's nothing incomparable with A, which is below B. That's really what it says. And then there's another result that we were able to improve upon. This is a result of Ted Slayman and Andreas Sorby from a few years ago. They showed that whenever you have two enumeration degrees A less than B, but A is a total degree, meaning it contains a set of the form A join A complement, or it is in the range of the embedding of the Turing degrees and enumeration degrees, whichever way you want to define it. Whenever you have A less than B, then any finite partial order embeds into the interval A from A to B. Okay, this is very much the opposite of density because you can actually have any finite partial order embedding. Now, if you make A equal to 0, it gets easier to state because what it then says is any non-zero enumeration degrees bounds arbitrary finite partial orders. There cannot be a linearly ordered initial segment in the enumeration degrees, basically, right? In fact, it gets as bad as possible. You can any finite partial order embeds. Okay, so those are the three results that we started looking at, and we looked especially at the one in the middle, and the one in the middle can be thought of as the following. So let me rephrase the result in the middle before I go to the next slide. So the result in the middle can be thought of as a lattice embedding. You have the two-element lattice, 0 less than 1. You map 0 to A, and you map 1 to B. And now we say every degree which is less than or equal B is either in the range of this embedding of the lattice 0, 1 or strictly less than A. That is another way of saying it. So that gave us the idea, oh, maybe we can extend this, and we were actually able to extend as follows. So this is the technical theorem that we were able to show. For any finite distributive lattice L, we can embed L called iota. There's an embedding of L into the pi02 enumeration degrees such that 0 of the lattice gets mapped to some degree A, say. The 1 of the lattice gets mapped to some degree B, say. And every enumeration degree which is less than or equal B is either in the range of the embedding or strictly below A. So it's the same thing as what Kent, Lewis, and Sorby showed, except that instead of having only the two-element lattice, we have an arbitrary finite distributive lattice, and we say anybody who is less than or equal B is either in the range of this embedding of this finite distributive lattice, or is actually below the bottom point of the lattice embedding. So that's a technical result that we were able to show in a priority arc, which I'll hint at the end a little bit, because it's an ugly zero triple argument. So look in particular, the way I phrase it may not be totally obvious, but just to reinforce this, the range of this embedding iota is, of course, an interval in enumeration degrees. So that gives us a coding of finite distributive lattices into enumeration degrees by intervals. In particular, that gives us this EAE undecidability result using a nice transfer lemma from a few slides ago. And also notice that, and therefore, any finite distributive lattice can be coded in this global degree structure with two parameters, top and bottom degree. So that gives us the EAE result. The eccentric embeddings result is a little more complicated to get from that, but one can actually, using that, and then there's some genericity argument, which is very reminiscent of the way these early decidability results for the AE theory were done. You can show also that that you can decide the eccentric embeddings problem, but I'll gloss over that for a moment, because I want to talk about what we were hoping to show. What we're hoping to show is actually something a little stronger. So first of all, instead of finite distributive lattice, we were really hoping for any finite lattice whatsoever. And we were hoping not just for a lattice embedding which maps the lattice into an interval, but we were hoping for basically the dual of what Lerman and Shor did for the delta 0-2 degrees. So we're hoping for an embedding of the lattice so that the top element of the lattice goes to a point B. Every element strictly between 0 and 1 of the lattice goes to some final segment of below B. and 0 goes to degree 0 in such a way that this is a lattice embedding. So therefore, you have, I mean, the technical result is stated here, right? So you have an embedding of the lattice L such that every enumeration degree which is less than or equal b is either in the range of iota or it is below the image of exactly one atom of L. So it's actually very strong result, namely all the atoms of L form pairwise minimal pairs. In fact, even stronger than that. But anyway, that's what we're hoping for. Well, if this had worked out, it would have put us a little closer to a decision procedure. We actually know that this would not have gotten us the full decision procedure for the AE theory, but it wouldn't have gotten a step closer. However, before we tried too hard, Maria and her student Jacobson-Grocott were able to show that our conjecture was just outright false, even for the 4-element diamond lattice. So here's the counterexample. If you have A and B, which are incomparable enumeration degrees, and suppose that that you have any enumeration degree which is below the join of these two degrees, and suppose that also that any x which is strictly less than A join B is either less than or equal A or less than or equal B, then if A and B have that property, that A and B cannot possibly form a minimal pair. Okay, this is the technical result that Jacobson-Grocott and Maria were able to establish, and that of course shoots down the conjecture from the green conjecture at the bottom of this slide here, even for the 4-element lattice. So back to the drawing board, we still hope to prove the following result, which is sort of more what you might expect, namely instead of having the word distributive in the main result from the previous slide, we were hoping for to drop distributive. You can show for any finite lattice there's an embedding such that any degree less than or equal b is either in the range of the embedding or strictly below A. So this would be a generalization there. This conjecture, by the way, seems to hold for more than just finite distributive lattices. In fact, there is this notion of interval dismantleable lattices, which I defined with some lattice theorists, Adaricheva, Hindman, and Nation. It is a sort of a version, a generalization of distributive lattices, which basically captures the idea of N5 and TPP lattice, if you remember what those are, and a bunch of other lattices. But for example, does not capture the 5-element module lattice M3. We currently have no good conjecture how one could decide the AE theory. So we have no working conjecture that is consistent with what we know to be true or false about the AE theory of the enumeration degrees. So therefore, this is basically hoping maybe somebody else has a clever idea how to do this. So in the remaining, what do I have? 10 minutes. Let me just say just a teeny bit about how you would prove the main technical result. Remember what we have to do for technical result. So we're given a finite distributive lattice L. We need to find an embedding into pi 0 2 enumeration degrees, which maps 0 to A and 1 to B, such that every enumeration degree which is less than or equal A is either in the range of iota, this embedding, or strictly less than A. So what are the ingredients? Well, I mean, there's a finite distributed lattices. So a special property about finite distributed lattices is that every element can be uniquely described as the joint of the joint irreducible elements less than or equal it. Here I'm calling 0 also joint irreducible just so I get this whole thing uniformly, okay? Now here are the requirements that you have to satisfy. So first of all, here's what you do. So for every joint irreducible element J in the lattice, including for the 0 element, you build a degree AJ represented by some pi 0 2 set, capital AJ. And then we define for an arbitrary lattice element, it's called a K, we define iota of K as the join of all the AJ, where J is a joint irreducible less than or equal K. So that clearly gives at least a lattice homomorphism, right? I mean, it gives a homomorphism into the structure. And then I call, let's say that this set here is represented by the set BK, which is just the join of all the AJ for J less or equal K, where J range, remember, over join irreducibles. So that's why J. And now here are two types of requirements that you have to ensure. So the first one is for any non-zero join irreducible element J, you have to show that AJ is not below the join of all the things which are not above J. And that can be said as follows. Look at the join irreducible J, look at the maximal element, the greatest element, which is not above J. By distributivity, there's a greatest element like that. Call that KJ. So what you have to show is you have to show that AJ is never below BKJ, no matter what choice of J you take. Well, for non-zero join irreducibles anyway. That's a positive requirement. And then negative requirement is the following. For any set X, which is below the top element, remember this is B of 1. 1 is the element of the one element of the lattice. And any non-zero join irreducible element J and L. So this is not exactly how we did it, but it's equivalent to how we did it, how we thought about it. You basically partition the thing as follows. You say, okay, either X is below BKJ, which is remember that the lattice can be partitioned into the ideal above, to the filter above J or the ideal below KJ. So for any choice of J, you look at the filter above J and the ideal below KJ, and you say, okay, either X is is below BKJ, which means you can push it down, or AJ is below X, which means you can push X up. And if you can do this for all irreducible elements, then you have the whole result. And of course, there's a number of conflicts which involve a zero triple prime argument. Notice that conflict in particular is between, if you look at, I don't know if you can see my cursor. Somebody maybe confirm if you can you see my cursor, Noam?
Yes.
Good. Okay, I say yes. Okay. So suppose you want to put something into AJ for diagonalization and keep it out. You want to extract the number from AJ for diagonalization and keep some finite set in the BKJ. Well, this is a problem if for the same choice of J, you have another set X, because this set X, as you take, so first of all, you would try here. You would say, okay, I want to try X below BKJ. So I take something out of AJ, which means I'm taking something out of B. But if I take some out of B, then of course that means that X can change. X can change negatively, and that means I no longer can, if I want to compute X below BKJ, I'm in trouble. So I can't do that. So instead, what I'm going to try to do, I'm going to try to code AJ into X. So it's a kind of like the Ahmad pair construction, except it's, you have to do it for multiple irreducibles all at once. And, the rest is a 10-page technical argument, but it's, it's what you would expect. Anyways, so I think this is probably a good place to stop. If there are any questions, I'll be happy to take them. Otherwise, thanks for listening. And you guys all stay safe.
Thanks, Steffen.
Yes.
Thanks, Steffen, for your talk. If anybody has questions, please just open your mic and ask questions. I think it's the easiest way.
So, is there upper bound for the pi2 theory of Turing degrees? I mean, do you know is it hyperismatic or arithmetic?
I'm sorry, say it again.
Is there an upper bound for the complexity of pi2 theory of Turing degrees or E degrees?
I mean,
upper bound. I mean.
Oh, I mean, so the pi2 theory of the Turing degrees is just outright decidable, right? So I'm sorry, I'm not sure I understand.
Sorry, about the E degrees. Pi2 theory is decidable, right? about the E degrees.
No, I mean, we don't know whether it's even decidable or not, right? But I
he's
think,
asking for an upper bound.
Oh, an upper bound. Oh, okay. Is there an upper bound? I mean, there is the theoretical upper bound, right? In terms of, I mean, just write down the complexity. Now, for the sigma 02 E degrees, I mean, the complexity is
No, sigma 02 I know the upper bound, but about the general pi 2
I do not know. No, I mean, I don't know. I mean, I don't know of a result that would give an upper bound at the moment. And in fact, this leads me to another question that somebody asked me when I gave a previous version of this talk. We do not know the complexity of the EAE theory. This is actually another interesting question that one might ask. I mean, because I mean, it's of course not true necessarily that the degree is bounded below 0 prime, right? Because I mean, there's no reason to believe that. It could be much more complicated. There is an upper bound for the global for the local degree structures, but for the global degree structures, I do not know of an upper bound. So
you don't even know what is arithmetic?
I don't. I mean, maybe other people. Richard is the one who's worked with this more than I have. And might be able to tell you, but I do not know a better upper bound.
Okay.
You can't interpret in some way in arithmetic?
I mean, I don't know. I'm sorry. I mean, I don't know exactly how you would do it. Yeah, sorry.
So you need to prove some basis theorem for the E degrees and get
right. Yeah, I don't know. I mean, the short answer is I really don't know.
Okay.
It's a good question, but I don't know. Yeah.
Okay.
Okay, are there any other questions?
Yes, I have an easier question. Did you try the M3 or the M5, whatever it's called, in the Pi 2?
So no, we tried, but we didn't try very hard because we mostly tried this to disprove what Maria and her student showed us was false. We tried this conjecture on the bottom here. So I mean, and actually it took it took Josiah and Maria not very long to figure out that this was false before we even got to final lattices. And after that, we just sort of gave up on that project because we will still work on finite lattices because because we're interested in this conjecture right here, for example, but we don't know. Yeah, I mean, we haven't looked very carefully at this because we've been busy with other things, and also, I mean, it took us quite a while to write this project up.
Right, but M3 is the test case, right? It's the easiest case for this.
That is obviously a test case, but that will be the very first thing that we will look at when we get back into the project. At the moment, we're all stuck with other projects, as you well
probably
know.
Start with an N5 sounds easier to me than M3.
N5, I am almost certain I can do because this is one of these interval dismantleable lattices where the technique that I described basically carries over almost verbatim. So I would say anything. I mean, you can look up my paper. It's just like a 3 or 4 page paper on interval dismantleable lattice on my webpage. I mean, any lattice like that, like N5. I mean, those are all almost certainly embeddable by the same techniques. We just didn't bother writing this up because we didn't need it. But it gets interesting with M3, and I don't know the answer. That's obviously the real test question.
Okay.
We tried. I mean, it wasn't for lack of trying. It's just we got stuck, and then we realized that there was this result by Josiah and Maria, and then we sort of like, okay, this isn't going to lead anywhere at the moment, so we decided to go somewhere else.
Okay, any other questions? think let's thank Steffen again.
I'll stop sharing.